All right. So far, we looked at Ohm's law and then the voltage and current sources. In this video, I'm going to provide an overview of Kirchhoff's laws. So this is going to add to your repertoire of circuit analysis skills. So we looked at, so far again, we looked at passive sign convention. Okay, if the reference current is along the direction of a voltage drop, then the relationship between voltage and current is positive. If not, it's negative. Right? Professor Aguilar showed here that when the voltage is plus and minus from top to bottom, north to south, and the reference current is from south to north, then it's a negative equation, negative sign in the relationship between I and R. Okay, and here, as Professor Aguilar explained, the voltage drop is from top to bottom, and the current is also from top to bottom. So you see that the IR equation does not have a negative sign, it has a positive sign. That's the passive sign convention. We saw that. Now I'm going to talk about Kirchhoff's current law and Kirchhoff's voltage law. Okay? Kirchhoff's current law and voltage law. Now, we use KCL and KVL to solve circuits. Okay? And you hear this term over and over and over again in this course. Okay? What does it mean to solve circuits? Well, it simply means we are finding out all the node voltages and all the branch currents. Let me show you what I mean. If I go to this circuit here, there are a bunch of nodes, right? 1, 2, 3, 4. I highlighted the nodes. Nodes is simply a connection point where more than one connections are made. Okay, that's a node right there because there is 1, 2, 3, 4, 5 branches coming out of it, 5 devices connected to that. Okay, that's a node. Same here as well. This is a node as well. There is a bunch of connections. Okay, there's a node down below and another node here. So what do we mean by solving a circuit? Okay, by solving a circuit, what we mean is to find the voltage at each of these nodes, VB. What is VC? Okay, and what is VD and what is VA? What is the voltage at each of these nodes? That's one part of solving a circuit. The other part of solving a circuit is finding the current through each of these branches. You see a connection between these two nodes right here. Okay, that's a branch, that represents a branch, and the amount of current flowing through this branch, okay, current in this branch through this resistance here. Okay, that's one of the variables we want to find out. So once we know all the node voltages and all the currents flowing through the different branches in the circuit, then we say we completely solved the circuit. That's what it means. Okay, so the two techniques that I'm going to give you, Kirchhoff's current law and Kirchhoff's voltage law, they help us solve the circuit, find the node voltages and branch current. Okay, typically what we do, and you will see this reinforced when we look at some problems, we often set up a set of equations. Okay, if there are 5 unknowns or 5 branch currents that we don't know, we set up 5 equations. These 5 equations we can solve simultaneously. If there are 5 unknowns from algebra, we know we need 5 equations. So we use KCL and KVL to set up those equations, okay, and solve them. So let's look at KCL. We'll start with KCL, Kirchhoff's current law, okay. Okay, the canonical definition of Kirchhoff's current law is that the sum of currents at any node is 0. So if you want to look at it in the formal definition of KCL, Kirchhoff's current law, it simply says when you sum up the currents, all the currents from 1 to infinity, all the currents that are at a particular node, they sum to 0. Okay, so for example, it doesn't matter if we look at what node, whatever node we look at. Let's take node A. Okay, if you look at the currents at that node and sum all of them, that would equate 0. That would equal 0. Okay, so that's the canonical representation. What you can do is you can use the directions, the polarity, such that all the currents flowing in, you can consider them as negative, having negative sign, and all the currents flowing out as having positive sign. So what KCL says is at node A, if you sum all the currents, what are all the currents at node A? There is I1, right? And that's leaving. I2 is coming in. And then there is, of course, I5 coming in. And then I4. Okay, what KCL says is, and what KCL is a manifestation of law of conservation of charge. Okay, what it says is at node A, if you sum all the currents I1, and it is positive because it's leaving, plus I4, that's a current leaving as well, then the current coming in is I5, so negative I5 and negative I2. If you sum all the currents at node A, that equals 0. Okay, so that is KCL, application of Kirchhoff's current law at node A. Okay, let me write it down a bit more clearly here, and then we look at the example of D. Okay, let's see. Let's look at another node D and apply KCL. Okay, KCL at Kirchhoff's current law at node D, right? So we look at the currents that are leaving. IC is leaving, right? And then I5 is leaving as well, and IA is leaving. So when you sum all the currents, IC plus IA plus I5, that equals 0. There's no current flowing in to this branch, to this node, so you don't have any currents with negative sign. Okay, let's do the same thing again with node A, right? We did look at node A earlier. Let me do that in a cleaner manner. KCL, Kirchhoff's current law at node A, right? Sum all the currents that are leaving, which is I1 plus I4. Those are the currents that are leaving. And then the currents that are entering are I2, okay, and I5. The currents that are entering, I show them with a negative sign, and all of that sums to 0. Okay, that's the idea of Kirchhoff's current law. Now, there is another way to apply KCL without worrying about sign, okay, positive or negative, okay, and that is looking at a node look at this particular node. Okay, let's see if I can pick a different color here. If you look at this node, okay, the way I like to apply KCL without having to worry about magnitude, without having to worry about sign, is by summing currents that are leaving on one side of an equation and currents that are entering on one side of an equation, equate them. Let me show you what I mean. Okay, at node B, there is current I1 entering. Okay, there is current IA leaving, right? IA is leaving. That's I3 actually. Current I3 is leaving. Another current IA is entering. IB is entering. And I2 is leaving. So what I do is look at all the currents that are entering. I1 is entering. IA is entering that node. And IB is entering the node. So sum them all up. IA plus I1 plus IB. Now equate that to all the currents that are leaving. I3 is leaving and I2 is leaving as well. Okay, the currents that are entering and then the currents that are leaving, if you add them on two different sides of the equation, then that is an application, that's a valid application of Kirchhoff's current law. Okay, so KCL at node B. Let's do the same thing. As a matter of fact, that's exactly equivalent to doing what we did earlier. Okay, so let's apply KCL at node C as well. Okay, at node C, look at the currents that are entering. There is one I3 current that is entering. Okay, IC is entering as well. And the current that is leaving is IB. Okay, so there is, and of course, let's not forget I4. There are three currents entering, I3, I4, and IC entering, and there is one current leaving, IB. Okay, now KCL simply says, and let me write it over here, apply KCL at node C, right? Applying KCL at node C. Look at all the currents that are entering. Okay, there is I3, I4, and IC entering, and that's equals to the sum of all the currents that are entering, I3 plus I4 plus IC, that equals the sum of the currents that are leaving, which is IB. Okay, that's the idea of KCL, Kirchhoff's current law. You can apply, again, there are two ways to apply Kirchhoff's current law, which is to use the sign convention. Treat all the currents that are entering as being negative and all the currents that are leaving a node as being positive. That is exactly the same. You would get the exact same result if you added all the currents into the node on one side of an equation and all the currents leaving the node out of the node. Okay, if you sum them up on two different sides of the equation, it will be exactly the same as using sign appropriately. Now we are going to look at this in a problem as well, but this is Kirchhoff's current law.